Okay, so we're recording. So you are used to using an x-axis and a y-axis, and your coordinates are x, y. You're used to working with points in the plane and using what are called Cartesian coordinates. Those are x, y coordinates. But sometimes in life and in applications, Cartesian coordinates are not the most convenient coordinates to use. And so we have other coordinates we can use to locate points in a plane. And when you go into Calculus 3, you're going to learn about coordinate systems for finding points in three-dimensional space. That's Math 280, multivariable calculus. But we're going to stick to two-dimensional space. All right, so what are these polar coordinates? All right, well, first we have to talk about what does it mean to plot a polar coordinate. And in figures 1 and 2, they talk about that, okay? So instead of an x-y coordinate, with polar coordinates, what you do is from the positive x-axis, you measure an angle theta, as you see here in figure 1. And that's just like in trigonometry, when you measure an angle theta, you do it from the positive x-axis. So you measure an angle theta, and then you move out, and then you stop at that angle, and then you move out from the origin a distance r, a radius, and you plot a point. And that point has the polar coordinates r theta, r theta. So you can plot points in the plane by identifying an angle, right? An angle could get you anywhere in the four quadrants, because you know, an angle can be like from 0 to 360, right? And then you move out a distance, a radius from the origin, and so any point in the xy plane you can plot using a polar coordinate. But one thing interesting about polar coordinates is that they're not unique. You can have polar coordinates that identify the same point. But we'll take it step by step. But in figure 2, what they have here is they have plotted two polar coordinates. One polar coordinate is r theta, and the other polar coordinate is negative r, negative theta. Okay, so what's that about? Well, with polar coordinates, you can allow your radius to be negative. You can actually have a negative radius in polar coordinates. And like what they've done here is that, so you know how the polar coordinate r theta, how that point came about in figure 2. But what about the other polar coordinate, negative r theta? Well, what they do is you measure an angle theta, but instead of moving forward a distance r, a radius r, you move backwards a radius r. And that's how you get negative r theta. Okay, that's how you get that. Are there any questions in figure 2? And we're in Appendix H here, H.1. So what we're looking at today, we're looking at plotting polar coordinates. And then, of course, we'll talk about curves and polar coordinates. But let's just take things one step at a time. So in the first example here, they want you to plot the polar coordinates that are given. So the first polar coordinate has, in A here, in example 1, has radius 1 and angle 5 pi over 4. Well, 5 pi over 5, what's pi over 4 in terms of degrees? Who can tell me what pi pi over 4 is in terms of degrees? 45 degrees. That's right, Cologne. So 5 pi over 4 would be 5 times 45 degrees, or 225 degrees. So do you see here in figure 3 how the first picture here, how they've plotted the polar coordinate 1, 5 pi over 4? Okay, so what they do is they measure 225 degrees, and then they move from the origin a distance 1, and that's how they get that polar coordinate. Let's look at B. On B, you have the polar coordinate 2, 3 pi. So I like to do the angle first and then measure the radius. So 3 pi, we know pi is 180 degrees. So 3 times pi would be 540 degrees. Okay, 3 times pi would be 540 degrees. And so one cycle, one full complete cycle, one revolution, I should say, is how many degrees? How many degrees is one complete, revolution? Going from the positive x-axis, measuring the angle from the positive axis, and one complete cycle going from the positive axis to the positive x-axis is 360 degrees. Good candy. So then if you go 180 degrees more, that gets you 540 degrees. So in figure 3, the second picture, they measure 540 degrees, or 3 pi, and then they move out a radius 2. Is there any question on the second picture in figure 3, where they graph the polar coordinate? All right, let me know if there are any questions. Okay, well now, for C here, they have the polar coordinate 2, negative 2 pi over 3. Well, now you have a negative angle. So you learned in trigonometry that positive angles, you go counterclockwise. Negative angles, you move you move clockwise. And that's what they have in the third picture. So pi over 3 is 60 degrees, right? So 2 times pi over 3 would be 120 degrees. So negative 120 degrees, they measure that angle in the third picture, and then they move forward a radius 2 in that direction. Okay. Are there any questions on the third picture? All right, well, then let's go to the fourth polar coordinate. Fourth polar coordinate is negative 3, the radius is negative 3, and the angle is 3 pi over 4. Well, pi over 4 is 45 degrees. 3 times 45 degrees is 135 degrees. So on the fourth picture here, let me just see what this is. Hold on here, one moment, class. It's just, okay, I don't need that. I guess that's just an enlarged image. I don't think we need that. I think you can see this okay. So, well, hold on here. One moment, class. Let me just try this. I mean, it's okay, but I can't see the whole thing. I'm just going to stick with this. And you have your ebook. You can look in your ebook too, right? So, all right, for D, you have a radius of negative 3 and then 135 degrees. So you measure out 135 degrees, but you don't move forward in the direction. You move backwards in the direction. Instead of moving forward at 135 degrees in that direction, you just move backwards. You walk backwards. You moonwalk backwards, okay, to a distance of 3. And that gets you at -3, 3 pi over 4. Okay, so you've just plotted, you've just seen how to plot some polar coordinates. All right, are there any questions on that? Okay, all right, well, let's move on then. Okay, so of course, with polar coordinates, you know, sometimes you want to take a polar coordinate and rewrite it as a Cartesian coordinate. And you can use these conversion, or you have a Cartesian coordinate and you want to convert it to a polar coordinate. Well, x equals r cosine theta and y equals r times the sine of theta. How many recall, and that's because cosine of theta is x over r, and sine of theta is y over r. How many recall those from your trig days, these formulas? They should be familiar to you. And they have that figure 5 below. Yeah, Rodrigo's seen it, Michael's seen it. You know, the cosine of theta is x over r, you know, adjacent over hypotenuse. Sine of theta is opposite over hypotenuse, y over r. Okay, so you know, nothing really new here. Nothing really new in figure 5. And then of course you have these also, you know, that r squared equals x squared plus y squared, and the tangent of theta is y over x. So these are just some basic basic knowledge, trig knowledge. Are there any questions before I go to a few examples? Okay, then let me go ahead and do that. So let me see here. Yeah. Let's do a problem here. Okay, let me give you a moment to copy this problem down. Okay, so here we want to find polar coordinates for a point that has these two Cartesian coordinates. So the -1 is an x, and the square root of 3 is a y. And for part A, we're gonna restrict our angle to be between 0 and 2 pi. But we want the radius of the polar coordinate to be positive. Okay? And in part B, we're going to find another polar coordinate that has the same location as the Cartesian coordinate -1 root 3, but its radius is going to be negative. So what's the best way to start a problem like this? What would be very helpful? What would be very helpful to have to start a problem like this? What would be very useful in trigonometry? What's very helpful when if you think to your trig days, what was really helpful when you would do your trig problems? A graph. That's right, Michael. So we're gonna have a graph here. So all right, I'll go to the solution here. Are we good so far? Okay. Okay. So here, what I've done with this problem. One moment. One moment. Hold on. Okay, what I've done is I've graphed the Cartesian coordinate -1 root 3. Okay, and we know that Cartesian coordinate lies in the second quadrant. And now I'm in the process. I want to find polar coordinates that will be equivalent to that. So first of all, what I do is I construct a right triangle here. Right? I construct a right triangle. Okay, right triangle. As you see. And I recognize that I have a 30, 60, 90 right triangle here. The 30, 60, 90, whoops, 30, 60, 90 right triangle. Sorry, you think I could draw that? Right? So 30, 60, 90 right triangle, I know that the hypotenuse is going to be 2 for that. The legs are 1 and root 3. The hypotenuse is 2. So, for the polar coordinate, I need to identify the angle, right? I need to identify the angle. Well, hold on, let me get this thing off. The angle, the reference angle for my right triangle is 60 degrees. So that means then that the angle for my polar coordinate would be this angle here, which is 120 degrees, because 60 and 120 degrees, 60 degrees and 120 degrees make 180 degrees. So that means that the angle is going to be 2 pi over 3. And then I move from 120 degrees, I move forward a radius of 2. And so that's going to be my polar coordinate, where the radius is positive and theta is between 0 and 2 pi. Okay, so let me just slow down a little bit. You might be copying that figure, so let me just slow down a little bit. Are there any questions so far up to here? All right. Well, now we'll look at part B. Part B, we want to find a polar coordinate, for that's going to get us this coordinate here, right? But we want the radius to be negative. So what I do is, I mean, the answer. Well, the angle that I'm gonna need is 5 pi over 3. Well, pi over 3 is 60 degrees, so that's 300 degrees. So what I did was I took 2 pi and I added pi to it. Okay, so I'm sorry, I took pi over 3 and I took 120 degrees. Sorry, I got to say this the right way. I took 120 degrees and I added 180 degrees to it. And that got me to 5 pi over 3. And so 5 pi over 3, this angle here, 300 degrees. Okay, I'm highlighting it in tan color, 300 degrees. At 300 degrees, am I facing the second quadrant or the fourth quadrant? If my angle is 300 degrees, and your quadrants, 1, 2, 3, and 4. For 300 degrees, am I think about yourself. If you were to row, just stand at the origin, stand like one place on the floor, and turn your body 300 degrees. You turn your body 300 degrees. Would you be looking in the direction of the fourth quadrant or the second quadrant? Good. Kahindi and Michael say the fourth quadrant. That's absolutely right. So think about it. You're looking in the direction of the fourth quadrant, but you're looking in the direction of the fourth quadrant. But what if you then were to walk backwards here, not forwards, but backwards, and I'm trying to draw it the best I can. Maybe I can use a different color here. Hold on. Let me use green. You walk backwards a distance of 2. Then that means your polar coordinate is -2, 5 pi over 3. Let me see, there's a question here, one moment. And then that puts you in the second quadrant. That's right, Kahindi. Okay, so positive radius means that you move forward in the direction you're looking. A negative radius means you move backwards from the direction you're looking. So I think about walking forward, walking backward, It's like, the Michael Jackson, right? The famous singer. He's passed away, but sometimes he would move forward and sometimes he would walk backwards, right? Right. Kahindi knows what I'm talking about. You know, that, what was it called? The moonwalk. He, you know. All right. So are there any questions on these two answers here? I'll make another comment too, because we are short on time here. But I want to finish just this comment here. So note that there are an infinite number of polar coordinates for a point. So like, for instance, like 2 and 2 pi over 3 is a polar coordinate. But if you add 360 degrees, which is one revolution, to the 2 pi over 3, if you add 360 degrees, you're going to get 8 pi over 3. So the polar coordinate 2, 8 pi over 3, is equivalent to the polar coordinate 2, 2 pi over 3. So 2 comma 8 pi over 3, that polar coordinate is equivalent to the polar coordinate. Well, I want to say it the right way. I'm not saying it the right way. To locate a point in the xy plane, there are an infinite number of polar coordinates that will locate the same point. The polar coordinate 2 comma 2 pi over 3 will, that point, that polar coordinate, and the other polar coordinate 2 comma 8 pi over 3, those two polar coordinates, you'll arrive at the same point in the xy plane. And also, here's another polar coordinate. If you had 2 negative 4 pi over 3, the polar coordinate 2 comma negative 4 pi over 3, you can instead of like instead of going counterclockwise 360 degrees, you can go clockwise 360 degrees. We do a revolution the other direction, and you get another polar coordinate. So there are an infinite number of polar coordinates for one point. And what I'd like to do, and thank you for staying a few extra minutes. Well, first, are there any questions on this example? All right, let me stop the recording then.